you. So, this is me. As was mentioned, I'm a comics journalist. So, first, I'm actually just going to talk about that for a couple of minutes and just kind of make the case for it. Because it's still something that's sort of new to a lot of people. And then I'm going to show you some comics and sort of give you a guided tour through some of the stranger impacts that humans can have on the changing world around us. Just a quick note on tools. I make all of my work digitally using a Wacom Cintiq, which you can see there in the picture I drew of myself. That's sort of a tablet that you draw on the screen of. So soup to nuts, I do everything with screens. So what is comics journalism? There's a little bit of a confusion of terms sometimes. Sports journalists write about sports, science journalists write about science. I do not write about comics. Think of it more like a radio journalist. I use the medium of comics to report. Fact-based, carefully sourced stories. And I produce a lot of comics journalism. It's my full-time job, and it's pretty varied stuff. I'm pretty lucky. I get to work on basically anything that interests me and catches my eye. That ranges from weird and strange things, like this piece on a bizarre medieval manuscript that's either one of the last great uncracked codes or loaded gibberish, to I do a lot of work in the Middle East, which is an area that I've lived in and traveled in a lot. But pertinent here, I also do a lot of comics about science, which is pretty much like working as a science journalist, but again, using the medium of comics. This is an excerpt from a piece that was published by a company called Medium, and I'll be showing some of my work with them later. And it's about how Australia is sort of like a giant sponge, and torrential rains there can be traced to a weird and previously unexplained drop in sea levels that happened in 2010. And for this, I got to interview a really awesome scientist named John Fasulo, who's a project scientist at the National Center for Atmospheric Research. And that actually brings me to probably one of the most fun things about being a science journalist, or even journalism in general. And that's that you get to interview academics and scientists, because they're really passionate people, and they tend to be really, really excited about their work. So that always makes for a really fun conversation. And then, of course, as a cartoonist, you get to draw them. So far, I haven't had anybody complain about that. And comics are actually a really great medium for communicating scientific concepts. Visuals and science go way back, of course. This is Audubon. Long history, but there's a difference between scientific illustration and using comics. And that difference is the element of storytelling. It's combining that visual component with a narrative. That has a really rich history too. Larry Gonick was one of the first people to use comics to write about science. He's a cartoonist, and he actually won a Knight Science Fellowship at MIT, a big journalism fellowship. He was the first cartoonist to ever win a journalism fellowship. He wrote the Cartoon Guide to Genetics, the Cartoon Guide to Sex, the Cartoon Guide to Chemistry, and had a long-running comic in Discover magazine. And in one of those comics, actually, he did a piece about my dad's research on sex change in fish. This is an excerpt from that in Spanish. It was originally in English, but I could only find a scan of it in Spanish. And when my dad told him that his young son, I was quite young at the time, loved to draw comics and asked them for tips, Gonick told him in jest to break my thumbs. My dad obviously didn't follow through with that advice, so here I am. And there's a lot of other science comics being produced these days. This is by a piece by Sam Woolman, who's an Australian comics journalist that ran recently on the Nib. Other names to look out for: Naki Naro, Lucy Bellwood, Sam Carbaugh. There's a lot of people doing really fantastic work. And it's being published in some places that are specifically devoted to it. Like the Nib and Cymbalia are places where you can go to find a lot of comics journalism. But it's really kind of spreading elsewhere. Popular Science, the BBC, New York Times have all run comics journalism. I've had work myself published in a lot of different places. And you really don't have to make the case for comics being a serious medium anymore like you used to. That fight was sort of fought and won a generation ago. And so I'm reaping those rewards, and I'm always very thankful for people like Larry Gonick that paved the way for that. But why use comics to report about serious things? Why is it so powerful? They take a really, really long time to make. So why choose them to tell a story instead of something else? And why do they work especially well for reporting on science in particular? First of all, there's the immediate experience. When you see a comic, you're drawn into it. You want to know more. When you see a field of text, you squint your eyes, it's a gray blur. So that's an immediate advantage that comics have, is that grabbiness. Somebody sees something on the web, it's got a visual, they want to look at it more. Also, that visual dynamic can make communicating difficult concepts easier. You see this in the huge rise of infographics on the web. This one is by a guy named Ivan Cash, and I included it because it's an infographic about infographics, which I thought was pretty funny. People really want to know stuff. Humans are curious, and they want help understanding it. And presenting things visually helps explain that. But what sets comics apart from infographics? It's the narrative. You give readers a thread to follow through the story. This is the key to it. It's a sort of hybrid form. And all of these things kind of combine to make comic journalism really perfect for the current media world. It's shareable, it's engaging, and it's captivating. I do a lot of work for KQED, the public radio station up in the Bay Area, and I've been told that my work for them is consistently some of the most popular stuff on their website. More and more editors are catching on. I've heard that from other editors. Colleagues of mine say that too. It's a really rapidly growing field. Essentially what I do for a living didn't exist 5 years ago, and now there's a bunch of us. So it's an exciting time to be in comics journalism. So now let's look at some comics I made about climate change, wildfires, extinction events, food riots, and melting cities. So this is going to be sort of an excerpted selection of some of my pieces. And I'm really especially fascinated by some of the maybe less noticed, less reported on effects of climate change and the human impact on the world. So I'll be sort of concentrating on that. But it'll be essentially pretty much a whirlwind tour through our impact on the systems that surround us. Some of this work appeared in Symbolia under a partnership with Years of Living Dangerously, the Showtime series. Some of it appeared on The Nib, which is a sub-publication of a company called Medium. And some of it was commissioned by KQED. And before I launch into this I just want to acknowledge that presenting comics as a slideshow is sort of an inherently awkward experience. They're really meant to be read. I'll be reading them while they're up there. I'll sometimes be summarizing, sometimes commenting, so just bear with me and enjoy the pretty pictures. I'm going to be presenting this in 5 broad sections. The first section is weather and earth. It's about weather, fires, and melting ice. So let's just jump right in. So anybody who knows anybody out east can attest to the fact that they've been getting more than their fair share of mega snowstorms lately. And when that happens, you'll always hear a few people talking about how global warming can be real since it's snowing more. But actually the opposite is true. A warming atmosphere, which is the result of climate change, is to blame for the expectation that snowstorms are going to get bigger and more dangerous in the coming century. So for this piece, I got to interview Dr. Kevin Trenberg, who's a distinguished scientist at the National Center for Atmospheric Research. And he told me that in general with climate change, there's an expectation that there will be more snow in the middle of the continent in the middle of winter. And that leaves a bigger risk of snowfall, and you're already seeing this on the East Coast. A warming atmosphere leading to more snow may seem bizarre, but the science is sound, and there's 2 main reasons for it. The first reason is that there's just more moisture in the air these days. So for every 1 degree Fahrenheit increase, you have about 4% water holding capacity increase. And the more water vapor that there is in the atmosphere, it holds more moisture. So that extra moisture feeds all weather systems. And what that means is that when it does rain and when it does snow, it rains and snows harder. And we're seeing this in many places around the world. And the second reason is that as long as the temperature is still below freezing, warmer winter weather actually can mean more intense snowstorms. Because the heaviest snowfall occurs when the temperature is just a little bit below freezing, not when it's really, really cold. When it's really cold, you can have this idea that it's sort of too cold to snow, and that doesn't actually exist. It's never too cold to snow, but it snows less when it gets really cold. At the same time, and this is an important idea, there's a really big trade-off between quantity and frequency. So the snow season is getting shorter at both ends. Winter is coming later and spring is coming earlier, but the intensity is greater when it actually does dump. So this is a big human effect. So if you have a region that's really accustomed to having a long, steady snow season, and instead of a short season where snow falls in huge drifts, it can overwhelm systems. This is water management, so it makes the issue of water management much more difficult. People in agriculture would rather have long, gentle rains than a huge deluge and then nothing. And snowfall's the same thing. If it all falls at the same time, it's really difficult to get rid of, and you don't really know what to do with them. They can disrupt businesses, knock out power grids, cause serious accidents. But the fact is, we're going to have to learn to adapt to them. One of the big things standing in the way of this is that the systems that we've developed sort of politically and on a local level are really designed for the century that they came into effect in, which is the last century. But the century that we're living in now is going to be very, very different, and our rules and regulations aren't really prepared for that right now. We're going to have to adapt faster than we've been adapting so far, and that idea is sort of a theme that I'll be returning to a couple times. So from snow, we're going to go to fire. So wildfires are nothing new in the American West, but their frequency has increased significantly over the past 30 years, according to a recent scientific report in Geophysical Research Letters. Interestingly, there's actually 2 regions where wildfires have decreased, and one of them is here in Mediterranean, California. The other is basin and range. They're still at a relatively high level in Mediterranean California, but just want to make that clear, this is kind of an all regions average. And they're growing bigger too. The total area burned had increased at a rate of about 137 square miles per year. And some of this can be actually traced back to fire prevention policy, which seems counterintuitive. So I got to interview Richard Minich, who's a fire scientist at Riverside for this. And he told me that this increasing fire frequency and size actually has to do with the effort to try to eliminate fire as a natural process in a climate where burning is normal. So fire is a vital part of the West's natural ecosystem. It's very dry here. And until about a century ago, most large wildfires burned unabated, and they would clear out the undergrowth in forests and make way for new growth. And there's actually a number of plant species that rely on fire to activate germination. But our treatment of wildfires really began to change a little over a century ago, in 1910. When there was this hugely devastating fire season, and millions of acres of forest land in Idaho burned, and scores of firefighters died, and it was a sort of huge shock to the system of the country. In response, federal and local land management agencies adopted aggressive fire suppression policies. This is where the whole kind of Smokey the Bear thing appeared for the first time. Michael Kodas teaches environmental journalism at the University of Colorado, and he actually used to work as a firefighter too. And he was telling me that the kind of idea at the time was that there was this concept that wildfire was this beast that you could just kind of eradicate. You could get rid of it altogether. And so every fire that broke out was just jumped on and put out. And that actually turned out to be really dangerous. It made fires stronger. And the reason for that is that it created this huge buildup of excess fuel in the forests, which resulted in many smaller trees and brush growing closer together. And one of the big problems here is actually the size of the trees, right? So if a forest is composed mainly of older trees, they're much bigger, they're further apart, and there's less opportunity for the fire to get up into the canopies of the forests. Once the fire gets up into the canopies of the forest, it can spread kind of from tree to tree really easily, and the whole forest goes up. It's pretty much game over. And with lots of younger trees packed in, that can kind of serve as a ladder that the fire climbs up into the canopies of the trees. So in addition to preserving valuable natural resources, aggressive firefighting efforts, and this is another big reason why we put them out so much, are influenced by suburban sprawl into naturally fire-prone areas. So the population in the West has exploded over the past century. We're living in more places than we've ever lived in the West, and those include fire-sensitive areas. It's a sort of especially difficult part of the story because it's counterintuitive. The thing as humans that we want to do the most is protect human stuff. But the human proximity to these dangerous fire areas makes control of burns more difficult because if there's a bunch of houses there, you want to, and there's a big fire raging through, even if having that fire rage through is maybe good for that ecosystem, it will get put out because you don't want the houses burned as sort of collateral damage. And climate change is having an impact in this too. And this actually brings me to something I want to bring up super quick as a journalist in general, is that one of the biggest difficulties in reporting on things related to climate change, you as a reporter, and especially your editors, always want to be able to say, is this because of climate change? And scientists are always really uncomfortable with that. And there's a really good reason for that. It is very, very hard to pinpoint a single event as being because of climate change. And this sort of has to do with the idea of a signal and the noise. All of our systems, weather, fire, oceans, etc., all have really huge variation built into them. There have always been droughts, there have always been extinction events, there's always been wildfires. That's the noise. And what you need to look for in this is the way that the entire system is moving. And that's where climate change comes into it. You're trying to look past the immediate events that can skew your data, can skew your understanding, and can skew your reporting, and see the trends. And that's difficult as a reporter, and it's difficult as a consumer of news. So moving from fire to ice. So the ground is frozen for all the year in much of the northern regions of the world. And because this ground doesn't usually thaw, it's called permafrost. And now, due to a warming climate, permafrost is thawing, and the ground itself is actually becoming unstable. And when there's a lot of things built on that ground, you've got a pretty big problem. So for this story, I interviewed Vladimir Romanovsky, who's a professor of geophysics at the University of Alaska Fairbanks, and he specializes in permafrost. And the interesting idea is it's a difficult concept to get your head around, but the building isn't sinking into the ground. The ground itself is sort of sinking. And it's happening any place where you have construction on permafrost. It's sort of a danger. It's happening in Fairbanks, Alaska. And it's especially happening in big cities in Russia with hundreds of thousands of people. This is a much bigger problem for Russia than it is for us. The biggest cities north of the Arctic Circle are all in Russia, but it's definitely an issue for us too. And permafrost covers about a quarter of ice-free land in the northern hemisphere. A lot of permafrost dates back to the last ice age, and it can be tens, sometimes hundreds of thousands of years old. Lately, the warming atmosphere has been dramatically accelerating its thawing. It's made up of a mixture of things, soil, rocks, ice, and organic matter, and that last part is key, and I'll come back to it in a second. But when it gets warm enough, the makeup of the mixture changes. That ice melts, and it runs away as water. So when the water runs away, the practical consequence of that is that the ground itself sort of settles. And it's a big problem because there's actually no insurance that covers damage from permafrost. So in areas that are in danger from it, there's sort of no recourse right now. But the thawing of the Arctic regions actually poses an even bigger threat than just infrastructure damage. So the last glacial period was about 12,000 years ago. 12,000 years ago. And there's organic matter sort of stuck in there. It can be the remains of plants and animals and all these things get trapped in the ice. More layers get put over it, and it's sort of like sticking a piece of pizza in a freezer, right? The food doesn't rot because it's cold there. But if you open the freezer up and it gets warmer, the food starts to rot. So when the pizza was in the freezer, or the animals were in the permafrost, they were basically out of the carbon cycle. And when permafrost thaws, that carbon comes back into the carbon cycle. And it sort of creates this vicious circle. A warmer climate thaws permafrost, which releases carbon, and that warms the climate. And then that thaws more permafrost, and that releases more carbon. So it's a dangerous feedback loop, and if this really starts accelerating in a big way, it becomes a big global problem. So moving on to part 2, which is feeding ourselves. So this is bringing it more kind of into a direct effect on our bellies. So for this piece, Heat Wave, I talked to Michael Hayes, who is the director of the National Drought Mitigation Center at the University of Nebraska. And we talked about the 2012 heat wave in the Midwest. 2012 in Nebraska was the hottest year on record. And in June and July, a heat wave swept across the central and eastern parts of the United States. Planting had gotten underway early, and everything looked great, and then suddenly there was this massive dryness and heat. And corn actually has its greatest vulnerability during its reproductive stages when it's sulking and tasseling. And they can withstand actually some pretty hot daytime temperatures, but it's really the warm nighttime temperatures that get them. And one of the big things that occurred during that heat wave was really warm nights. So it catches the corn at this really sensitive time in its reproductive cycle and devastates it. And we are the world's largest supplier of corn. So with the crop failing in much of the Midwest, the price of corn skyrocketed more than 50% in about 5 weeks. And agriculture obviously depends on weather. Crops need water and sun to thrive. Planning ahead and good harvests keep food affordable, but the weather is changing and planning ahead is getting harder. And this ties back into what I was talking about earlier with the systems we'd set up for water management being outdated, being planned for a century that is no longer really the century that we're dealing in. We planned for the way things were, but things are changing really fast. The changing climate could make extreme weather events stronger, longer, and more frequent. And so in a recent paper for the American Meteorological Society, scientists estimated that human-caused climate change quadrupled the likelihood of that 2012 heat wave that ravaged the Midwestern corn. Rising global temperature is projected to reduce the annual crop yield by up to 2% every decade for the rest of the century, according to, report is now published at the time it was leaked, but the UN's Intergovernmental Panel on Climate Change. Well, that same report projected that population growth will cause demand for food to rise by about 14% per decade. So there's a basic kind of mismatch here. Yield is going down, demand is going up. And the poorest regions of the world are the ones that this hits in the biggest way. They spend the highest percentage of their income on food, and that means price spikes hit them especially hard. And when food prices actually get high enough, they can lead to political instability. In 2007 and 2008, rising food prices helped spark riots around the globe. And actually, as a side note here, there's a really interesting case to be made that some of the social factors leading into the explosion of the Syrian civil war can be traced back to a massive drought that hit the Levant between 2006 and 2011. 85% of livestock died, and there was a huge influx of poor, rural, and suddenly jobless people from the countryside into the cities. And that's a pretty good recipe for massive social unrest. But it's an issue here in the US too. According to Dr. Hayes, when the price of food jumps more than your grocery bill is affected, it's hard for livestock producers because they use corn to feed their animals, and ethanol plants going out of production, which then has an effect on communities. You can kind of think about this like when the auto industry moved out of the Rust Belt. It isn't just the plant itself that is affected, it's the stores that depend on the people who have money to spend at those stores. So when industry in a place is affected by something like an ethanol plant closes, it sort of ripples out through the community. So let's bring this a little closer to home into California. Because of its sunny climate and rich soil, we produce about $45 billion worth of agricultural output per year. And that makes us the biggest farm state in America by far. More than a quarter of the state is farmland. Over a third of American grown vegetables come from California, and the state produces more than 2/3 of the nation's fruit and nuts. But agriculture needs more than a sunny climate to thrive, it needs water. And we're right now faced with a drought of historic proportions. 2013 went down as California's driest year on record. That's from NOAA, by the way. And these dry times are really big problems for California's agriculture. So out of all the state's water that is allocated for human use, about 80% goes to agriculture, and the remaining 20% goes to commercial and residential use. Many farmers letting their fields fallow, which can cause jumps in food prices, and can affect jobs too, and it's that same ripple effect that I was just talking about in the last piece. As the drought continues, some farmers are considering what they grow. Acreage devoted to cotton has been dropping in California in recent years. That's a very water-intensive crop. And switching irrigation methods is one way to kind of squeeze a little bit more out of the water that you have, but it has high upfront costs. And one way or another, agriculture will have to adapt to drier conditions because we're now entering it's the 4th year of this drought. So part 3, hot water. So sea levels are rising. Most people know that. The global sea level has risen about 7.7 inches in the past 140 years. It's currently rising at an average rate of about 0.12 inches a year, and it's getting faster. By the end of the century, scientists project that sea levels will have risen by about 2 to 7 feet. And to put that in perspective, about 5 million Americans live less than 4 feet above the high tide mark. I'm going to get back to that in a second because it's a little bit misleading. So there's 2 main reasons why this is happening. The first one is obvious, right? Melting glaciers. We hear about this all the time. It has a big effect. There's a lot of water trapped in glaciers, and when they melt, that water moves into the ocean. More water in the oceans means higher global sea levels. It used to be on land, now it's in the oceans. It's pretty obvious. But there's actually a big second reason that's a bit more complicated. The oceans are actually expanding as they warm up. Global warming has raised the planet's temperature by about 1 degree Fahrenheit, and that warming melts ice, but it causes thermal expansion to happen. You see, the warmer water is, the faster its molecules move. And as the molecules speed up, volume expands, and that means that the same amount of water, if it's warmer, takes up more space, and sea levels rise. And warming and expanding water accounts for actually about half of global sea level rise so far. So it isn't all land ice going into the oceans. And also, another big thing that a lot of people don't realize is that rising sea levels aren't evenly distributed. Some areas will be much more effective than others. The OECD published a list of cities with most threatened assets due to future sea level rise. And just super quick, I want to make clear that this is most threatened assets, so that kind of skews the data a little bit because richer places obviously end up higher in the list. But number 1 is Miami, number 3 is New York City. It's 2 American cities in the top 5. And there's a lot of different reasons for why sea level rise isn't uniform. Some of it is land subsidence, but the bottom line is that different places are affected differently. And what is the effect of this? Well, one thing is that higher sea levels mean bigger storm surges and flooding when bad weather hits. So think about Hurricane Sandy. It's tough to say whether Hurricane Sandy itself was caused by climate change. That goes back again to that idea that a single event is difficult. But what you can say for sure is that the water in New York Harbor is about 12 inches higher these days than it used to be 100 years ago. And a whole lot of that is due to climate change. So when a storm surge happens, when those big waves come, those big waves are a foot higher than the systems that were designed to contain them are. This sort of problem is not only going to get worse, but it's also closely tied to those ideas that I was talking about dealing with excess snow and things like that. So, shell shock. Carbon dioxide levels are also increasing in the world's oceans. Higher levels of CO2 make seawater more acidic, and that makes it harder for animals that build shells to make their homes and can lead to disease and die-offs. There's a lot of animals that build shells. There's also a lot of animals that build skeletons, like coral. Those aren't technically shells out there. But tiny shell-based organisms are part of the diet of big marine animals like salmon, and that can place entire ecosystems at risk. Those tiny shell-based organisms that I'm referring to, by the way, are pteropods, and they're about the size of a pea. They're really small. And everybody loves to eat them. This increased acidity could be traced back to one primary source, and that is us. And here's how it works. So carbon dioxide is released by human activity into the atmosphere. Everybody pretty much knows that. But about 30% of that CO2 ends up in the oceans, or rivers, or lakes, bodies of water. And that CO2 dissolves and reacts with seawater, which is H2O, to form carbonic acid, which lowers the pH, which increases the acidity of the ocean. But that's not the whole story, because oceans are already saturated with another compound called carbonate. Organisms use carbonate to create their shells and structures. And the problem is that when carbonic acid from the CO2 breaks down, it releases hydrogen ions, which then bind with the carbonate that the organisms need. And then that means that carbonate isn't available anymore, which means they can't use it to build shells, and existing shells can actually dissolve. And so to put this in perspective, oceans are about 30% more acidic now than when the Industrial Revolution began. And this increased acidity is already starting to have a human impact. So for this, I actually got to work with my sister-in-law, Lauren Summer, who's a fantastic science reporter at the KQED. She interviewed Terry Sawyer, who co-owns the Hog Island Oyster Company. And he was talking to us about hatchery collapses. So a few years ago, the hatcheries in Oregon and Washington, which supply them with baby oysters, which are really tiny, they just look like miniature versions of oysters, began seeing huge tanks full of larvae die off. And the problem was they were filling their tanks with seawater. So the increased acidity of the ocean combined with a natural upwelling of that. And to be clear, upwelling is a natural process on the West Coast. It brings cold, sort of nutrient-rich, lower pH water up to the surface. You can rely on it happening and you can account for it. And species are actually adapted to survive it in normal upwelling conditions. The problem is that it's now coinciding with the anthropogenic effects of the CO2 from the atmosphere. It's being absorbed into the oceans. So that devastated the young oysters after they filled their tanks with the seawater, and there was huge die-offs. And just like the oysters that he grows, Terry Sawyer says he'll have to adapt to the rapidly changing environment. And he told us we don't have the luxury to look the other way. Our challenge is to figure out where we can grow, what we can grow, and what adaptations we can implement. And that's a really important point to keep in mind, is sort of resilience and adaptation. Which brings me to my last section, ecosystems and extinctions. So one of the biggest immediate effects that we're encountering in this new world is the massive and rapid loss of biodiversity. Entire species are dying out at unprecedented rates. We're in the middle of what is sometimes called the Holocene extinction or the sixth extinction. So it started with megafauna around 10,000 years ago into the last ice age, and it's been a pretty steady drumbeat ever since then. But it's lately been accelerating at a pretty alarming rate. And this is caused in part by climate change, and in part by more direct human activities like hunting or other things. And I'll end this presentation with two comics showing two very different paths to a profoundly changed ecosystem. But the thing that really unites them is human responsibility. Here's the Busy Bears. So in 2006, on Banks Island in northern Canada, Jim Martell shot a really strange-looking bear. It was different from the polar bears that Martell had been hunting with a license up there. It had patches of brown fur and a shoulder hump. The bear's DNA was tested, and the results made headlines. This is from the BBC. It turned out that it was the hybrid offspring of a male grizzly bear and a female polar bear. So, polar bears and grizzly bears aren't usually known to get romantic with each other. Hybrids had occurred before in zoos and in captivity, and there's been reports of them unconfirmed going back a ways, but rarely, and they've never been confirmed before in the wild. And there's a pretty good reason for this. Their territories only really overlap a little bit. Grizzly bears hunt on land, and polar bears hunt on ice. And another big, really important point is that bear mating is not sort of a one-off thing. Both polar bears and grizzly bears, who are pretty closely related, need to spend several days together before the female begins ovulating and reproduction is even possible. So Martel's bear was not the product of a one-night stand. There's still some big debates about naming. Growler bear has been suggested, grizzly bear, polar grizz, and nanowak, which is a combination of the Inuit words for grizzly bear and polar bear. But so far, grizzly bear seems to be winning out for better or for worse. And grizzly bears have characteristics inherited from both parents. They have the shoulder hump, that big shoulder hump, the grizzly bear, the white coat coloration of the polar bear, the brown fur of the grizzly bear around the eyes and around their claws, and then they have really long kind of grizzly claws. And unlike other hybrids, such as mules, grizzly bears are fertile. And this is actually a common misconception about hybrids. We're most familiar with mules, and so we assume that hybrids are infertile by nature, but that's actually not true. It's pretty much a toss-up. And grizzly bears are fertile. We'll get to that in a second. So since that first confirmed hybrid, more and more grizzly bears have been appearing in the north. Another was shot in 2010, and DNA tests showed that it was actually the child of a grizzly bear, which means that its grizzly parent was, it's really funny to keep saying this, was successful enough to mate and produce offspring. There's also been many sightings, both by researchers and by First Nations communities. So what is going on with all these grizzly bears? Well, according to Brendan P. Kelly, who is the co-author of a 2010 article in Nature about Arctic hybrids, by the way, he's actually now the director of conservation research and the chief scientist at the Monterey Bay Aquarium, since I did this piece. It's a big part of it is climate change. So the Arctic is changing really fast, and it's not just the temperature that's changing. The whole habitat is changing, which creates a lot of different pressure on the organisms. And he gave me this great analogy. So you have the two oceans, right? And there's this big barrier between them of South America. And imagine if you just sort of melted South America. There would suddenly be this massive exchange. This has happened a couple other times in history when kind of continents come together for the first time. There's always sort of a big free-for-all. And there's tremendous opportunities for a species to interbreed. And with losing all that ice in the Arctic, which is sort of a natural barrier, it's like you lost a continent, but it's happening very, very rapidly. And that makes interactions between the two species much more likely, but that's really not the only reason for grizzly proliferation. Another big part of it is the fact that polar bears are actually adapted to the sea ice, and with advancing sea ice, that reduces the number of polar bears. So he told me to think about it like a bar. Say you're a Republican, you want to go home from the bar with a Republican. But if you're stuck in a bar with only Democrats, the chance that you'll go home with a Democrat are high. So if there's 10 grizzly bears and 10 polar bears, they'll probably just mate amongst their groups. But if there's one polar bear and 10 grizzly bears, that one polar bear might end up mating with a grizzly bear. So hybridization on a wide enough scale can actually lead to the extinction of one of the parent species. There's a few documented examples of this happening. One is mallard ducks in New Zealand in the 1860s. They were introduced, they began mating with the native gray ducks, and eventually the native gray duck population was basically entirely subsumed, and few if any native duck populations remain. And it's not just a grizzly problem. Kelly and his co-authors identified 12 possible interspecies hybridization between other Arctic mammals. One thing you'll notice about this, by the way, is that they're almost all aquatic. That's because that barrier was mainly kind of a barrier between Arctic seas. So the beluga and the narwhal, the narluga. The right whale and the bowhead whale, the right-head whale. The harbor porpoise and Dahl's porpoise, the Dahl porpoise. The ringed seal and the harbor seal. I'm not even going to try that one. And there's more. I encourage you to check out this great paper in Nature. And he said that the easy fix, of course, is to slow down the rate of warming that's disintegrating this habitat. And if that's the easy fix, then one shudders to think about the difficult fix. So the Arctic is changing rapidly, and the Pisleys and other Arctic hybrids may be the inheritors of what it becomes. So my next piece is actually it is yet unpublished, so this is a cool sneak preview for all you guys, and it's about python hunting in Florida. Burmese pythons first arrived in Florida as exotic pets. A few dollars in the 1970s would buy you small snakes. But they grow fast, up to 10 feet in their first year. And they can be dangerous, even deadly. And of course, not all Burmese pythons are deadly pets. There are many people that really love their pythons, and they will yell at me on the internet. But they are big, dangerous wild creatures that can grow up to 19 feet long. Can be a little overwhelming. And so by the early 1980s, enough overwhelmed python owners had released their unruly pets into the wild to establish a breeding population in the Everglades National Park, which is give or take an hour's drive southeast of Miami. By the time biologists in the park and rangers had started taking notice of the snakes in the early 2000s, it was basically already too late. The snakes had been seen in the park dating back to the 1990s, but they were always just assumed to be sort of one-offs who wouldn't be able to find a mate and would thus die out without being too much of a problem. The Everglades python population, however, is now estimated to be in the tens, perhaps hundreds of thousands. So I got to talk to a couple grad students for this, actually. Thomas Selby, who's a grad student at the University of Florida, and he's contracted to work with USGS, which, despite the name, does a lot of work that's not explicitly geological. They do a lot of studies of invasive species, too. And he told me about pythons. They're ambush predators. They'll find a game trail or watering hole and just kind of post up, which makes them hard to detect, therefore hard to control. And he works on a project directed by Kristen Hart, testing python population control methods using implanted radio tags. And what they're actually testing, as a quick side note, is the Judas method, which is one of my favorite names. So that's basically tracking an animal somehow, in this case with radio tags, during mating season, to have it lead you to other animals that want to mate with it. Then you capture or kill those other animals. And this has actually been used, I think it was used to get rid of the pig populations at the Channel Islands recently, which is a big controversy. But so same general idea. And pythons have been observed engaging in big social mating behavior in the native habitats in Southeast Asia. So the hope was that it would be a good way to find a lot of snakes at once. Hope did not work out so much. I'll get to that later. So on March 6, 2012, Selby and his coworker and fellow grad student, Brian Smith, were out looking for a Burmese python implanted with a radio transmitter. It's this sort of big thing you hold above your head and it beeps until you get close enough. It's like a horror movie. So Selby said, I heard a movement. We looked down and we saw this massive python moving off. And they actually saw the other snake they were tracking too, moving off in the other direction. But it was an entirely different snake than the one they were tracking. Selby grabbed the python's tail to stop it, which is how you catch a python. Kind of grab its tail like that. There's some really fun videos of that online. And then Smith distracted it away from biting Selby by provoking it to strike at him again and again and again. They wrestled with it for Selby told me, about half an hour, 40 minutes with this giant snake. Finally tired it down, Brian Smith, this is Selby speaking still, grabbed it by the head. It was like a 170-pound noodle. And they were in this horrible habitat. It was almost half an hour getting out of there carrying this 170-pound snake. Then to cap it all off, when they scared for it, they shut off. And the python turned out to be a whopping 17.6 feet long. At the time, it was the biggest python ever found in the Everglades. There have since been, I think, 2 found even larger than this. It's also more than twice as big as the largest native snake. And this kind of gets me to one of the big problems with the pythons. And then when the python was finally euthanized about a month later, it was found to be carrying 87 fertilized eggs inside of it, the most on record in Florida. And Selby says that's what makes pythons such a great invasive species. They have a lot of babies, and these babies actually have a really high rate of viability too. So a significant percentage of that 87 would have survived, been able to breed, and they would have had a bunch of babies too. And when python babies come out, they're only a little smaller than the largest native snake species at its largest. So that's why they're so good at surviving. So this is Selby again. You have this unchecked predator in an ecosystem where it's thriving. They'll eat anything. Native birds, alligators, deer, basically whatever they can fit into their mouth. And they actually aren't much of a threat to humans ourselves, they're responsible for only 5 recorded attacks on people in the Everglades between 2003 and 2012, including one on Thomas Selby in 2012. Different snake, he has a crazy job. But they pose a profound danger to the region's fragile ecosystem. And you can see this in the native mammal population. So the way they did this study was actually using roadkill, which is a pretty great way to track mammal populations. But it's been crashing. They compared 2 different periods between 1996 and 1997 when there were pythons in the park, but there weren't very many of them, they weren't established. In 2003 to 2011, after pythons were known to have established, and the mammal decline is astonishing. Raccoons are down 99%, possums are down 98%, deer are down 94%, bobcats down 87%. So I talked to Brian Smith about this, the other guy who caught that enormous snake, who's also at the University of Florida. And a general principle, this is him, in community ecology is that more diverse communities are more stable. And there's a couple different ways to think about this. So like, if the pythons are eating a lot of bobcats, maybe that means that the bobcats were hunting rats, and there's a huge explosion in rat population, and the rats start eating all the native bird babies. Or if the raccoons or the possums are prey for larger predators, and the pythons are eating all the raccoons and all the possums, there's less prey for these other larger predators. So it's not just what the pythons eat, you can have these kind of ripple effects out through ecosystems. And it's really too early in the situation to know for sure what the effects will be. This is a really recent phenomenon, the python effects. So different methods have been tried to control the pythons, including pheromones, trapping, radio tracking pythons during mating season, the Judas method, and snake sniffing dogs, including a beagle named Python Pete. That's him right there. Unfortunately, nothing's had much success. It's really difficult terrain. Dogs are a little better at finding them than humans, but you still have to manage to get through the Everglades, which is really hard. And so efforts are now focusing on stopping their spread. Estimates of potential ranges differ, and there's a little bit of a spat right now in the community study of this. Rhoda et al. Put out a paper based on studies of native habitat in Southeast Asia, that's the orange part, estimating that you basically get all the way up the East Coast, all the way up the West Coast, all the way down through Central America. This was countered by a paper from Pierre, I hope I'm pronouncing his names correctly, et al., which gave a much more limited range, basically the Gulf Coast of Mexico and the southern tip of Florida. This was then countered by another paper from Rhoda, revising their estimates and challenging the methods that Pierre had used. As Brian Smith told me, it's probably somewhere in between. So the bottom line is the python population is still expanding to the north. And they usually end up at the top of the food chain anywhere they go. It's the hypothetical diet, courtesy of National Geographic, of about 5 to 7 years in a python's life as it goes from being a baby to a full-fledged adult. But they don't end up on the top every time. They had 2 pythons implanted with radio tags getting eaten by gators during the study. And Sylvie ended up having to stick his arm down the alligator's throat to retrieve the tracking equipment in its stomach. It was like some old-timey circus show. But occasionally ending up as an alligator's lunch won't be enough to stop the pythons. And pythons are by far not the only uninvited guests wreaking havoc in Florida. That's a nutria, lionfish, which are a huge problem, Brazilian pepper tree, a Cuban tree frog, a giant African snail, the ambrosia beetle, which is also a big problem. There's just kind of a rogues gallery, but there's a lot. Florida is a hotbed of invasive species. But all put together throughout the entire country, invasive species cost the US more than $120 billion in damage and control costs. And it brings me back to that sort of lesson that humans enact profound change on the ecosystems that surround us, whether it's by design or by accident. And that's it. I'd like to end though with a quick note on the title of the talk, which I call Drawing the End of Our World, because I think that's an important distinction between that and drawing the end of the world. The systems that surround us are not coming to an end. They are changing, and they're changing because of us. And the problem is that all of our civilizations and all of our cultures and pretty much everything we value and hold dear came to be under a very specific set of circumstances. We are adapted to the climate and ecosystem that surrounds us. Its predictability is what allowed us to flourish. And that predictability is changing now, and we're going to have to change too.